been a while since I was this excited about servers. Yes, servers, not serverless, because Vercel's new fluid compute thing is actually really cool, and there's a lot we can all learn from it, whether or not we are using Vercel itself. I have a lot to talk about here, from the history, from how we moved from Lambda over to servers again, why Vercel built this, and all of the AI stuff that led to us getting here in the first place. Believe it or not, AI is a huge part of why this new compute primitive is necessary. And once you understand how it works and the incentives that got us here, it might make a lot of sense to you. Even if you don't end up using it, there's a lot we can all learn from this new model, and I'm so excited to dive in. But since Vercel doesn't pay us anymore, a quick word from today's sponsor. If you like shipping slowly and taking your time, today's sponsor's not for you. For everyone else, you should definitely check out Blacksmith. They'll make your builds 2 times faster or possibly even more, and they've done it with some really cool, crazy hacks. We can talk about how easy it is to set up. It's literally just this one line of code change, but what really matters is the things they did to make it so fast. They found a fun hack that I'm surprised more server companies haven't. They're using gaming CPUs. Gaming CPUs are much better at single-threaded performance, which makes them much better for everything from Docker builds to actually compiling your code. And these numbers aren't theoretical. They're showing real wins in real projects. PostHog's Docker builds went from 8 minutes to 1 minute 27 seconds. Nodes went from 3 hours to a little bit under 2. And both saw massive reductions in cost as well. It's important to note this isn't just for JavaScript. Obviously, Node is built in C++, but they have custom caches for pretty much every language you would reasonably use, from Go to Ruby to Python to even Zig. And they'll do anything for performance. They're building their own storage architecture that's up to 4 times faster, and their cache is way bigger too, 25 gigs instead of GitHub's measly 10. If you think this is too good to be true, I get it. Thankfully, they offer you 3,000 minutes for free, no credit card required. Go set it up today. Tell them I sent you. Thanks again to Blacksmith for sponsoring. Check them out today at swadev.link/blacksmith. Before we get to fluid compute, we need to talk a little bit about the stages of compute that we had before. First, we had traditional dedicated servers. Hopefully, we all understand how these work. You have some software, sometimes an image of software like a Docker image that is being hosted on a VM or a computer dedicated to whatever you're doing. So dedicated servers are actual computer or VM on one, always on, handles traffic in parallel, needs to be scaled manually. This is the key part. I'd say these two are the key things to know. The dedicated server by default is always on. If it isn't, then you're going to have to wait some time for it to be provisioned, because if, I don't know, you want something like preview deploys. If I go to the T3 chat repo and find some random branch in here, you'll see that all of these have a really useful preview link where I can click visit preview, and this will bring me to a temp URL that is just this branch hosted so that we can go play with this new build that Mark just did. These things are great if you have a model of compute where you don't need a dedicated server for every version of your app. But if you're using traditional dedicated servers, that means every single branch needs to have its own box dedicated to it. It also means if you have more users than you expect, you need to spin up more boxes. And if you have less users, you need to either move to a cheaper box or spin it down. The fixed cost model of dedicated servers kind of sucks if your workloads aren't fixed too. If you have a traffic pattern, like, I don't know, during the day, you have a ton of traffic. So we start the day with a lot of users, but then at night it goes down a whole bunch. And then once the next day comes, it starts again. And we have a server that's capable of this much traffic, or we can double the performance to a more expensive server that goes here. What are your options? Because this sucks. Either you pay for this server all the time, try and guess when the traffic's going to go up and move to this, knowing that some users are going to hit an error if you don't scale properly. Or do you just always pay for this more expensive one, even though half the time your traffic isn't close? This isn't great. And that's why we ended up in the wonderful world of serverless. It's also often known as serverless functions. The reason they're called serverless functions is they're not a traditional box. So they should be treated as stateless. If you need state in your serverless functions, the state should go in something like a database or Redis or something. So they're stateless. They spin up on demand, and they die when not being used. And most importantly, they scale automatically, because the scale is more instances are spun up as more users are using the thing. And once a user's request is done, it dies. If you were to think of this example in terms of serverless, instead of there just being one line, think of it as a literal infinite number of these lines, depending on how many users you have. And when a user makes a request, one of those boxes will spin up, or one that's sitting around will be used, resolve their request, and then die in 2 seconds if it doesn't get hit again. Cool, awesome, fine and dandy. There are a lot of catches here, though. The difference we care about the most today is this one. Each instance can only serve one user at a time. So when a user is hitting your website that's hosted via serverless, they get a compute node. They get a VM dedicated to them in that instance. When the request starts, it either spins up or reserves allocation on something already spun up, generates the response, sends it to them, and then that can now serve other people's requests. This is great in the sense that you don't worry about scale, but the key is, where is the concurrency handled? Concurrency and parallelism is handled with dedicated servers in the server, and if you need more servers, you'll spin up more of them. Whereas in serverless, the concurrency is handled entirely by spinning up new VMs. The concurrency layer, like the place where multiple requests happen, is higher up. It's at the VM layer, so multiple VMs are spun up per user. Instead of within your VM or within your server, multiple threads are spun up per user. So if we think of this as like a box, and this box is a VM instance, does the concurrency live inside of or outside of it? If it's a traditional dedicated server, then we have slots in here effectively for each user, or in Node, you have the event loop, which actually makes it pretty good at handling a lot of throughput at a time. So with a traditional server, we can have user 1 or A, B, C, D, E. So all of these users are in the same server. Now if we have user F, they can either wait for A to be done and go in, or a new instance can be spun up that handles F as one of its threads. With traditional servers, the concurrency and parallelism is handled inside of the VM. If you need more, you spin up your own additional VMs using something like Kubernetes, Terraform, whatever you want to do to orchestrate them. Cool, awesome, you can do that. The difference between this and how it works in serverless is each serverless instance has a lot less going on in it. So you could think of it as individual tiny VMs that are just serving the individual user's requests. So you might have one of these for A, B, C, D, and E. And since all of these are their own users serving their requests at whenever they want, if a new user needs something and all of these are busy, cool, it just spins up another. You never have to worry about concurrency. However, now you're paying for each user's compute. Let's move these so they're over time instead. We got A, then B, then C. Let's say C is shorter and it resolves earlier. If this was a traditional server, all of this is being served as part of one server. I'll call it dedicated server to be clear. We have this dedicated server. User A makes a request. User B has a request too that comes in. Since we haven't hit our max handling here, we're good. And if I put, let's say we make it so this can handle 5 at a time. So we have A, B, C, D, E. If F comes in after one of these resolved, we'll say it comes in here. That's fine because we don't have too many things going on. But if it comes in here, we can't fit it anymore because all of the space this server can handle at once is being taken. But there's a huge benefit here. We have to think about how much it costs. If all 5 of these users are making a request, we'll say that A takes 2 seconds, B takes 2 seconds. Let's say all of these are 0.5. The bill here wouldn't be for 2 plus 2 plus 1.5. The bill here would be for the whole time it's being used. So you would be a little under 2.5 seconds here. But now we don't have a place to stuff this other request. If we change this to not be dedicated servers, instead be lambdas, all of these can happen in parallel, and it doesn't matter because each of these is being scaled without our thought or effort at all. So F can just come in whenever it needs to. It doesn't matter anymore. The problem is, even if the requests come in this way, they're not billed this way. The requests are billed like this because you're paying for each VM's usage time for each user. This costs a lot more than that does. So why would anyone ever use serverless? There's no way the benefits outweigh the negatives here, right? Because that just seems insane. You're paying for 2.5 seconds here. You're paying for 6 seconds here. Just why would you ever do that? I'll show you why. Because we spent the last 5 years doing everything we could to reduce this down to as little time as possible. When I first deployed Ping using the T3 stack and tools like Prisma, our request times could take 2 to 3 seconds, especially if it had to spin up Prisma, connect to the database, and then start responding. It wasn't fast. So we put a ton of effort in, as the whole industry did, to do everything we could to make these requests faster. Instead of having the data far away from the server, we co-located so it wouldn't have to take as much time doing it. Instead of fetching all of the data all the time on every request, we started caching more aggressively. We did all of these things with the goal of reducing the time it took for these requests to resolve. There were 2 reasons for that. Obviously, the cost savings that I've indicated here, but also because it's a better experience for your users. If a request takes half a second instead of 2 seconds, your site feels much, much better. So we've spent the last however long doing everything we could to make these numbers a lot less like this 2 second and a lot more like this 0.5. Hell, for something like upload thing, it's even lower. Our P95, so for 95% of our requests, they're under 300 milliseconds. So server or not, the compute's not the expense at that point. But upload thing isn't our only product. We now have T3 chat, and the average request time's a good bit longer. You might be catching on to where we're going now. The serverless model makes a lot of sense if your requests can be really short. But what if one of these requests, instead of it being B or whatever, it's AI, chat, stream? Do you know how long these take, guys? Some of the models we have can take over 800 seconds. That's insane. It's crazy how long these AI chat responses can take. And it doesn't matter how fast your database is anymore. It doesn't matter how close the database is to the server anymore. It doesn't matter how well optimized your render paths are, how well cached your stuff is. Streaming an AI response can take minutes. Let's say you're building an AI chat app and your request looks something like this, which is the reality for most of these AI chat apps, us included with T3 chat. The average request time isn't measured in milliseconds anymore. It can be measured in literal minutes. And if we have a dedicated server, this is fine, because on a dedicated server, this request isn't doing anything in its time. It will get a single word back from whatever AI model provider you're using, and then quickly forward that back to the user. The crazy thing is Node is actually a really good solution for this, because you're just constantly waiting for the AI servers or providers to send the next token that you then send down to your user. So most of the time is spent waiting, and the actual compute you have to do is very, very simple. It's just forwarding the data you got from the API down one piece at a time. But with Lambda, we can't do this. With serverless, in the traditional way you would use serverless on Vercel, we couldn't do this. That's why the future is so exciting. That's why fluid compute is so cool. Because instead of all of these being summed up, instead of paying for 50 seconds of compute while users are sitting there waiting for responses, what if one Lambda could just respond to multiple requests? We'll get there in a second, but there's one more tangent I have to go on, which is streaming in the first place. This is T3 chat. It's the best AI chat I've ever made. Try it out if you haven't. I want to show you guys how streaming works by using this. So we click on the little chat here and you'll see these come in one token at a time. It's effectively one word at a time. And that's why the UI can update as things come in, because it's all being streamed from the server. Why do you care about this? Why am I even bringing it up? Streaming is a huge part of why Vercel bothered making all of this in the first place. Vercel really wanted streaming for server components, because server components would block until the compute was done. So you'd be sitting on an empty page with a little loading bar on the top, waiting for the chunks to come back from the server. So they wanted to have streaming so you could send some of the HTML and then send the rest when it was done. Awesome, cool, super hyped they did that. But there was a problem. Lambda didn't support streaming. Lambda, which is the main way people use serverless, it is the official serverless solution on AWS, kind of the inventing of the whole paradigm and way of building. They didn't support streaming. This is a big problem, because if I make a request to the AWS gateway, it spins up a Lambda. The Lambda resolves my request, sends a chunk down, and then it dies. The problem is the gateway couldn't process a stream. So as soon as you sent one token, one chunk, one line to the gateway, it said, oh, cool, you're done. I can shut you down now. And the user would get one word of whatever the response was supposed to be before the server dies. Entirely unusable. So how did they solve this problem? Well, it turns out Lambda actually has two modes. Mode one is request response mode, which is a user makes a request to a URL. The gateway on AWS realizes, okay, this URL needs this packet, this code to run. So it takes that code and sends it to the Lambda. Once it's spun up, it sends the request to the Lambda. And once the request has generated a response, it sends that back to the user. And then it dies. The problem was this mode didn't support streaming. So they had to use another mode, which is API invocation. This mode doesn't work great for request response. API invocation mode doesn't work great for request response because the Lambda doesn't spin up when the user makes a request. So now you have to build your own layer in front that will handle the request coming in, figure out where it needs to go, spin that up, generate a response, find some way to get the message back, and then send it to the user. And this is exactly what Vercel did. So if we have our box of Lambdas and we have our user, and as we all know by now, users are circles. Traditionally, we had a very, very thin layer here that was the AWS gateway. this super thin layer would take the request that you sent, either find a Lambda in here that can solve your problem or spin one up if there isn't one, send the request there, get the response back, and as soon as it gets the response back, it sends it to you and it sends a kill request saying, you can die now. And if it isn't dead by the time the next request comes in, it'll keep using that same Lambda. But this isn't forming an actual connection. This is like an HTTP call to the Lambda, basically just forwarding the request over, getting a response from it, and then sending that to the user. There is really no logic here. This AWS gateway is effectively just a switch statement, figuring out where the code should go. Vercel's solution here was actually pretty clever, and I'm surprised I haven't seen more people trying to clone it yet. They built their own edge, and this edge is a little bit thicker. That also means, to be fair, it's a little bit slower than the gateway. If you compare the edge performance, especially between the edge and the actual boxes that are fulfilling the edge requests, it's not as fast as it is something like Netlify, where they're a little better co-located and a little simpler overall. But the Vercel edge does things a bit different. The Vercel edge takes the request and sends the spin up command, but it doesn't forward the request over. I'm going to change these arrows to be a different color. We'll make them green so you know that those arrows are the ones that are dedicated directly to what the user is doing and seeing. So we don't send a green arrow over. We'll use a yellow for arrows that are the service saying do things. So this says spin up to tell Lambda to spin up the thing. It responds saying spun up. But part of the spin up request is it gives it something to connect to. I don't personally know the details of how it does this connection, so I'm just going to pretend it's a WebSocket. I don't know if it is or not. We'll go with it. Once this spins up, it forms an actual connection. We'll just call it a WS connection. It forms this connection from the Lambda to the edge where your request came from. Once this connection is formed, it will then send your request down using that connection, and then it can send the response however the hell it feels like. It can send it immediately. It can send it as multiple chunks. It can do whatever. This is also why they were able to introduce things like wait until. Wait until can only happen, and if you're not familiar, here's a real example of a wait until inside of our actual production T3 chat code. This is wait until post-hog promise. I do that because we want to track usage so we know how many models are being used and how they're being used. We don't want to block your response on that. And if I hit awaited this here, like await post-hog promise, now you don't get a response until that's done. That sucks. I don't want to have to wait for post-hog analytics to complete before you see the results. But wait until, which is a functionality largely pioneered by Cloudflare, but now it's in a lot of other things, specifically in Vercel in this instance. Wait until says, hey, by the way, don't kill me till this is done, please, so that when the request has been responded to and the user's gotten their response, we can continue processing other data. So just because they got a response doesn't mean the Lambda's dead. If we have things we want to do, like log it, we don't have to wait however long it takes for this to run for the user to get a response. Previously, if we had just done this after, the server might have died and this response might not have gone through. Now you don't have to worry about it. So you might send all of these things down this WebSocket connection. The first one, it'll be the request gets sent, and then we'll just say this chunk 1, chunk 2, last chunk. And maybe there's a database on the other side here. Like we'll say this is my post-hog analytics. After it's done, it still can be alive for a bit and send the event over to post-hog, even though it has completed this here. And the reason it can do all of that, and the reason that we can stream requests from a Lambda to the user, the reason we can run things in the background, the reason this Lambda hasn't died yet, all of that is because they abstracted their edge layer from the Lambda. So instead of letting AWS do their thing with their gateway, where we send it a request, it handles all the Lambda stuff. They do it themselves programmatically in order to use Lambda in that other mode, form a connection to the Lambda that isn't just send it a request, get back a response, but an actual back and forth live connection with it. That now lets us send the chunks to the user, one piece at a time. This all enabled streaming, which was a huge, huge, huge win. But that's not all it technically enables. So if the Vercel edge now is connecting to the Lambda, does it really have to spin one up? If we're not using this model where the gateway spins up a Lambda, resolves it, and dies, maybe the Vercel edge can hit a Lambda that's already live. What if instead the Vercel edge checks to see if there's a Lambda already going, makes sure its CPU utilization isn't too high, sends you there, and responds to it there? Now, all of a sudden, you don't have to serve one request per Lambda at a time. That's nuts. And that's what the in-function concurrency they did earlier this year was. Everyone's favorite, the serverless servers. The way it works, I think they have a diagram in here, is, they have their function invocation service, which is their edge thing I was just showing, and it sends out requests to different function instances. The problem was there were points where on your server, it might not be doing anything in that Lambda. So if I'm waiting for the database to respond, that Lambda's not doing anything. And theoretically, another user request could be processed while you're waiting for the database to respond. But instead, the server would just sit there and wait, and you have to spin up new ones for other users. The in-function concurrency allowed them to check how much traffic a server was getting, and if it wasn't getting too much, send another request that way. But it was very much a hack on top of the traditional Lambda invocations, where the Lambdas would still be your Lambda with your code for your project, and it could take multiple requests at a time. So to visualize this, instead of being billed for all of these sequentially, if theoretically you could fit multiple at a time on the same box, it would. It would be pretty limited to how many it could do, but you could easily get like 2 to 4 requests on one box at a time. And now instead of paying for the 10 seconds for all 4 of these requests, which would have been 40 seconds of billing, you only have to pay for here to here, which by the looks of this here would be like 12 to 13 seconds. That's a really big win. And it's cool that one Lambda can effectively serve multiple requests at once. And a lot of companies saw a pretty sizable win from this. The customers they tested with were seeing a 20 to 50% reduction in compute usage by turning on this new in-function concurrency stuff. Really cool and awesome. But there is still a catch. As I was saying before, with these 10-second requests, most of the time it's doing nothing. So imagine like there is a chart here. I'll just draw it like this. We have green is it is busy. Red is it's not really busy. It's effectively idling. So it might be busy right at the start for all of these, doing actual compute, verifying your cookies, dealing with tokens, whatever else. Not much, but there are some. For pretty much the rest of this request, it is doing almost nothing. So if it's at 100% utilization for the first fifth of a second, and then it spends the rest at 1% CPU utilization or less, you're still paying for the 100% CPU for this window, which sucks because a 10-second request, even if it's using 1% of your CPU, you're still paying for 10 seconds. Maybe it can run in parallel and work with others as well. Cool. Awesome. But since you have a dedicated Lambda resolving just your request, you still have to pay for that box being spun up and running. What if this was way more flexible? What if instead of that Lambda just serving one customer's request or one like backend's request, one function's requests, it could serve way more people? What if it could serve more than one developer at a time? What if it could prioritize, depending on the different traffic patterns, who is having their request responded to on that server? What if you got this so efficient that you didn't have to charge for the time in red at all? Funny enough, this is actually how Cloudflare works. Cloudflare's product is really interesting because Cloudflare workers don't isolate the way either of these things do. A VM instance can isolate by giving you different threads for each of your things. The serverless solution, serverless gives you a dedicated VM for every request. In-function concurrency will let you resolve multiple requests for one person on the same server. Workers isolate in a weird way. Workers isolate in a VM, kind of, but the VM is V8. You know, the JavaScript engine that most of our browsers are using. Technically, I'm not because I'm on Zen right now, but when I hop back to Vivaldi, or you use Node, or any of these other things, V8 is the JavaScript engine that powers the world. And one of the things V8 can do really well is isolations. So it has different isolates, they're called, which are the like different tabs in your browser, where each of the tabs has JavaScript that can't touch the JavaScript from the other tabs or the memory those are using, but you can have one instance of V8 serving all of these other pages safely at once. And if most of the pages are sitting there doing nothing and 2 are doing a lot, it can handle managing that with your CPU really well. So the way Cloudflare works is they're using V8 as the isolation layer on their servers. So when a user goes to my service on Cloudflare, it grabs the JS file needed to respond to them. It loads it the same way your browser would, while a bunch of other different developers on Cloudflare stuff is running next to it. But the V8 layer is letting it solve your request. And if your request takes a while, but most of the time it's not doing compute, it can spin up more other customers' requests. And that's why they price it the way they do. On workers, you get a limited amount of CPU time, which is the amount of time it's spending actually working. So think of it as like the code you're running, doing the work. Like if you're generating an image or you're signing some signature, the actual CPU work. Even if your request takes 5 seconds to respond, most of the time it's going to use a hell of a lot less, probably closer to 10 to 30 milliseconds. On an upload thing, for example, we're using workers to make sure you get to the right file. Our average CPU time for those is like 8 milliseconds. It's nothing. Even if the request time takes longer, it doesn't matter because Cloudflare doesn't get affected by that. If my request takes 30 seconds and it's only computing for 10 milliseconds, it can handle other customers' requests on the same box, in the same VM, in that 10 to 30 seconds that goes on. Also, the 30-second HTTP request, that's CPU time. There is no duration limit. A worker could run for days, and it doesn't matter as long as it's not using the CPU the whole time. This is a really compelling model for things like the AI streaming stuff. And I was actually about to pull the trigger and move because our bill wasn't bad on Vercel. In-function concurrency made it pretty hilariously cheap. It was literally 1/100th or less of our bill from Claude and Anthropic alone. It was like under $100 for all of the T3 chat usage to this date. Cloudflare's would have been even cheaper though, because they only bill for when the CPU is working, which it would be doing almost no work for us. Vercel finally figured out how to do this themselves. That is what fluid compute is. If you turn on the switch in Vercel, you will no longer be billed for idle time. You will now only be charged for the time the CPU is actually working, and it can handle things way more parallel, way better. No more VM per request. Now the compute being used, it's fluid. I actually do really like the name, as silly as it is to use liquids for computer names ever. The amount of compute being used goes up and down depending not on how many requests you have or how much those requests idle, just by how much CPU time is being used. So this has been like 3 generations of concurrency. Gen 1 was dedicated servers, where the server does the concurrency. And if you need more concurrency, you spin concurrency up with multiple additional servers. You had serverless, which was concurrency at the server invocation level. We had Cloudflare workers, which was serverless at the VM isolation layer. Kind of a gen between, but timelines doesn't work out as well. You have the in-function concurrency, which we showed here, where if your functions are idling, it can do more things on that box, but it's still billing you for the whole time. But this final frontier, fluid compute, and also the way Cloudflare workers effectively work, you're only billed now on CPU time. And now the concurrency isn't based on the threads on your machine. It's not based on the idle time in your request. It's not based on the number of servers you have. It's based on your CPU utilization. That's phenomenal. You're actually just billed on how much CPU you use. This allowed them to make a bunch of really significant changes. As soon as this dropped, I enabled it. An interesting thing is max duration. The default max duration on Vercel is a lot lower than 300 seconds. I forgot what it was. We had to keep bumping it because certain AI providers were so slow. The users' responses weren't getting hit because the timeout was being hit instead, which sucked, especially because you had to consider we were paying for the whole duration of this request. Not great. One of the cool changes with Fluid Compute is now the default is 800 seconds because it barely matters anymore. They're handling all of that on their side. As they say here, traditional serverless wastes idle time. It fails to efficiently utilize available resources during periods of inactivity. This is the thing Node is really, really, really good at. Even if JS is single-threaded, it handles I/O really well. If something else is going on and you have to wait for it, you can do other stuff at the same time. That's why async await is so cool. That's why .then was magical. That's why JavaScript is so powerful on servers and why it's actually quite surprisingly fast. That's why the default max duration of 15 seconds was so unacceptable, because if a request takes 15 seconds, it's not doing a bunch of compute for that 15 seconds. It's almost certainly idling for most of it. Now, in that time, it can do other things, and I'm way less scared to bump that max duration up, which is why they do it by default now. Fluid maximizes available compute time, which optimizes your computer footprint and also resource efficiency. So if you want to save electricity being used, technically this helps there too. A lot of people saw 50% plus wins with this. I saw one person had an 85% reduction in their costs in compute usage, which is just insane when you think about it. It also helps prevent cold starts, which is dope. If we go back to our metrics for it, it's pretty insane. I've already saved 20% compute. Memory utilization's been fine. 99.8% of our requests are served hot now. That's huge. That means that almost every request is hitting a box that's already running. Whew. So good. So cool to see. We now get the benefits of auto-scaling and pay-as-you-go pricing without the price being as exponentially higher, without things like AI streaming apps killing our bills and destroying our user experience, without all the problems that, funny enough, we had spent the last 5 years solving, AI made it so we have to deal with them. All the effort that Vercel and all these other companies put in to making requests respond faster doesn't benefit us if we're taking minutes to send a streamed AI response. So they solved the problem. And they used all the tech they had already built for handling streaming, for handling serverless requests, and for handling all the craziness between the two, is now given to us, and they're forwarding the cost savings along too, which is unexpected and really cool. It's kind of crazy when you think about Vercel just effectively cut their compute income by as high as 80%. That's nuts. But their goal here is to not make you worry about your CPU bill if the CPU doesn't need to be running in the first place. And they're forwarding this cost over because they don't want to make all their money reselling a ton of wattage being wasted in an AWS data center. They want to make their money off actually providing value and also off this AI wave. And this change makes them the best serverless provider for AI stuff. And it also, in my opinion, finally makes them competitive with Cloudflare for streaming. I saw a question in chat from a very well-respected person, Naman. I'm not going to be able to find it probably. I saw other things from him. I can't find the specific message, but he had asked, why didn't I go with Cloudflare if it's so much cheaper for these things? The main reason I didn't do Cloudflare is it's not Node. Cloudflare is running their own V8 isolate layer, which means you give up a lot of random things. Things like file system access. You just don't have it at all anymore. A bunch of random packages that are annoying to set up. I spent a lot of effort to get it to even work and deploy on Cloudflare, and I got it mostly working. But as I was doing that, I started hearing about the fluid compute stuff, and I was like, okay, I can wait 3 days. And it dropped, and the performance is nuts. The benefit of Cloudflare for me is a lot lower now, because I don't have to give up Node to have those scaling characteristics anymore. And that's why I'm hyped about this. That's why I actually really like fluid compute, and why, even though I'm using Cloudflare a lot more recently, and I'm using Netlify a lot more too, if I have requests that take minutes to respond that also benefit from Node, this is the best way to do it. It's kind of crazy that your bill will be cheaper deploying on Vercel than it would be doing this yourself on AWS, because setting this all up yourself sucks. And I know that because I talked to the engineers who did it. They spent the last 4 years figuring this all out. A lot of people are asking, why isn't this on by default, which is a good question. There are theoretical cases you can hit where it might cause problems. Malte is the CTO of Vercel. This has been his baby for a while. I remember talking to him about this stuff years ago. This is what he had to say about it not being on by default. There is an observable change because each function may handle multiple requests at the same time now. So again, if you wrote your code in a way where it expects just one request at a time, doesn't cut it. If it expects multiple at a time, you're fine. From the thousands of customers who have tried the beta, I'm aware of 3 cases where this was an easily fixable problem, hence the need to enable it. So 3 people had a problem where they had to change their code to make sure it was safe for this new type of concurrency. I would love to see those code snippets. I'm so curious what cursed stuff people were doing. My guess is it was something like let user ID equals some ID, and then this global was being used in multiple places. Like, that's pretty much the only case I can think of where you could hit it. But people write a lot of bad code. I'm not surprised. This is a little demo that they made to show off Fluid Compute. There's a little send request button here. When you hit it and Fluid Compute isn't on, you see each request gets its own box unless it's finished, and then it can go to the existing one. But if I keep hammering it, we keep getting new boxes. That sucks. I'm gonna refresh it. Now Fluid Compute's on. Do you understand the difference here? We're not spinning up a new box per request. That's huge. That's insane. It's so cool that we now have a way to spam requests on just one box and not be billed for each request, instead being billed for the compute used in total. So good. This visualization is also really, really good. Yeah, this is the right way to do compute. I'm so excited to see the whole industry start copying this. I'm loving it. Yeah. And as Lee said here, that's not even a simulation. It's hitting real functions, which is admittedly why that test site I just showed isn't live, because it costs a lot of money to run a test like that. But it properly showcases the benefits of this model. Pretty nuts that Tom was able to get that working for real. The only catch is, at this point in time, it only works for Node and Python because they've had to build their own runtime. This isn't a traditional runtime like Dino or Bun is. It is its own layer before the function code runs, so it will still run actual Node in it. It's this custom Rust layer that is the thing actually running on the servers, the Lambdas they're using, that makes all of this possible because they can much more easily hot swap things in and out when requests are being processed. I can't believe they got it working in Python as quickly as they did, but you can see this really is an AI bet. And as I mentioned before, wait until, which necessitates some abstraction on top of Lambda. One quick acknowledgement, because I think it is worth calling out. Fluid is a new compute model, but it is built on a lot of other things that have been done in the past, specifically Google Cloud Run, which is Google's equivalent of Lambda, had this day zero. They were right. Whether or not I would ever have recommended anyone bother setting up Google Cloud products, especially Cloud Run, that's a conversation for another day. To their credit, I've been talking with more people over at Google, especially the startup program. They've been awesome to work with. And some of the AI stuff, especially AI Studio, is surprisingly good. But I would personally never deploy or recommend deploying on Google Cloud in its current state. It's not great, but they have good ideas within there. And Google Cloud Run was one of those good ideas that took 30 plus steps to link to a GitHub and deploy it. And it also has crazy weird rate limits that aren't visible to you and other issues. But Cloud Run had this idea first where it would spin up a server if there wasn't one. It would use the one that's already spun up if there was, even if it's still serving someone else's requests. It's cool to see them acknowledge that. And I know a lot of Google employees are hyped right now, dropping told you so's. And honestly, they're right. They had the right ideas. A auto-scaling server with a serverless interface that figures out how to route your functions. That's like the end-all be-all of compute. This is, as far as I can tell, the best compute model for Node.js that I can theorize, that handles peaks and valleys of traffic, that handles Node and its concurrency, that handles the fact that you're idle half the time waiting for a database to respond, and handles the crazy long requests that are crazy low compute for AI stuff. This seems like they found a really, really, really good balance. And I am so hyped to start using this for all of our production flows going forward. Let me know what you guys think. Is this just another Vercel ad, or is it actually a pretty impressive product? I think this makes a lot of sense as the final frontier of how isolation and specifically concurrency have evolved in the server world. And it makes serverless a lot less painful to use. Let me know what you guys think. Until next time, peace nerds.